Hi everyone. So in today's lecture we are going to deal with oscillations and waves. Now these two, if we club them, you know that it is a very big topic, and whatever videos you will find available on YouTube, you will be seeing them at least of 2 hours or 3 hours if we combine both, right? But here I'll try my level best to complete the whole portion in as less time as possible. My target would be to finish it say within 1 to 1.5 hours. Let's try and see that. So I have made the notes in such a way that the explanation part I will be dealing with as fast as possible, covering most of the important topics of these two chapters, right? So let's start with without wasting any time. So here first we talk about oscillations. Now about oscillations, what we know, oscillations is a case of periodic to and fro motion about a stable equilibrium position. Stable equilibrium position means where the net external force is 0, net torque is 0 and the total energy remains conserved, and energy obviously will remain conserved, but at stable equilibrium position the potential energy will be minimum. So that condition we call as stable equilibrium position. So about stable equilibrium position, there will be to and fro motion under the effect of some restoring force. So there should be some restoring force which will try to bring it back whenever it is going away from the mean position. Now the simplest form of such an oscillatory motion is what we call as SHM. SHM, simple harmonic motion, where the restoring force at x distance from the mean position, if you take the mean position as x equals to 0, then at x distance from the mean position, the restoring force is given by vector form minus kx vector. So x vector is directed away from mean position, so force will be directed always towards the mean position. K is known as the force constant of SHM. Now when we write K as the force constant of SHM, so force being mass into acceleration, so acceleration at that particular position can be written as minus k by mx vector or minus omega square x vector. But we know acceleration is double derivative of position, so we can express this SHM equation in a differential equation d square x by dt square, taking this minus that side, so plus omega square x is equals to 0. So when we represent in vector form, then this minus sign is of importance. Otherwise, if you are writing the magnitude, you only know that acceleration and displacement are opposite in direction, then no need of writing minus sign. For vector form representation, we use this minus sign. Goes that side, so this is differential equation. I hope it is clear. Now here the expression which we have written minus k by mx as minus omega square x. So omega, which is root k by m, is called as the angular frequency of SHM, which can be written as 2 pi f, where f is the frequency of SHM, or you can write it as 2 pi by capital T, where T is the time period. So time period is 2 pi by omega, 2 pi under root k by m. So if force constant is known, if you are able to relate the force at x distance from the mean position in terms of x, then the coefficient of x will be called as force constant. So 2 pi under root k by m will give you the time period. Now this motion will get exactly repeated. When we say exact repetition, means not only the position, the direction of motion should also be repeated. Collectively this term we call as phase. When we say phase is getting repeated, means position and the direction of motion both are exactly repeated. So that will occur after a minimum time interval which is called as capital T, which is time period. So every capital T time interval later you will see the repetition of phase. So we can say that the motion gets repeated exactly after every interval. Delta T is n times capital T. N is an integer 1, 2, 3, 4. Means at t equals to capital T, t equals to 2t, 3t, 4t and so on. You will see the repetition. Okay. Next, if we draw the SHM on a straight line, we call this type of SHM as linear SHM. When we draw the SHM on or represent the SHM on a straight line, say x-axis, so here we have three important positions which you need to be careful with. One is called as the left extreme position, one is called the right extreme position, and exactly midway we have mean position. Mean position we are taking for our convenience as origin x equals to 0, right side x equals to a, left side minus a. So a will be called as the amplitude of SHM. At both the extreme positions, velocity is 0 and acceleration will have maximum magnitude. How much is that? Omega square capital A. From the formula omega square x, omega square capital A. On the right extreme, the acceleration will be towards mean position, that is left. At left extreme, acceleration will be towards mean position, that is right. At both extreme, velocity is 0. At mean position, acceleration is 0, whereas speed is maximum. Why speed is maximum? Because mean position, I said, is stable equilibrium position. Stable equilibrium position means total potential energy is minimum here. But in SHM, energy remains conserved, minimum potential energy means kinetic energy should be maximum. So speed will be maximum over here. Okay, so V maximum, acceleration 0, speed maximum. A, as I said, is amplitude. In general, at any instant t equals to t on this line and in between the extreme positions, the position of the particle can be represented as a sin omega t plus phi. Omega t plus phi is called as the phase angle. Velocity is dx by dt, which we can write as a omega cos omega t. So if you square both and add, then you will get v square equals to omega square a square minus x square, one of the most important equations of this chapter. V squared, speed at any position x, can be found by v square equals to omega square a square minus x square. What is the maximum speed? If you put x is equals to 0, maximum speed magnitude will become omega a. Remember this? Okay, next, as I said, omega t plus phi is called as the phase angle of SHM. We are representing it as theta at time t. Phi, which I said omega t plus phi, here this phi will be called as the initial phase or phase constant. Why? Because if you put t equals to 0, theta will become equals to phi. Note x and v, as you saw that position and velocity, one was sine, then other became cos. Sine and cos always differ in phase by pi by 2, remember this. And who leads? Always cos leads sine by pi by 2. If you forget, very easy trick to remember, sine becomes 1 at 90 degree, whereas cos becomes 1 at 0 degree. So who has attained the maximum value earlier? You will say cos. So what is the gap between them? Pi by 2. So cos leads sine by pi by 2, remember this thing. So when we have cos theta, we can always write it as sine omega t or sine theta plus pi by 2. So cos theta can be written as sine theta plus pi by 2. So here phi is called as the initial phase. X and v differ in phase by pi by 2. V and a also differ in phase by pi by 2, because acceleration, again you see, acceleration became minus omega square x. So if x is positive, acceleration is negative. So they have a phase difference of pi between them. X and a have a difference of pi, x and v have a difference of pi by 2. So a and v also will differ in phase by pi by 2. Now minimum time, this thing I tell to the students, simplest technique, no need of using phasor diagram or anything, directly you can find minimum time required to go from any position to other position if they ask you. So from mean position to any position, say x equals to x, or from x equals to x to mean position. How we will find? Very easy. Minimum time you will just see is theta by 360 into capital T. So the total time period can be divided by unitary method. 360 degree is the complete phase angle. For that you take capital T time. So for theta phase angle you will take time how much? Theta by 360 into T. Now how to find theta? Sin theta is x by a. So from mean position to go from mean position to any position x, or from x to mean position, simply find sin theta is x by a. So time taken will be theta by 360 into t. As simple as that. See example. Mean to, suppose a by 2, plus a by 2 or minus a by 2 I want to go. So basically here one thing more we should add, we have to take the mod value here. So when you are going from mean to a by 2 or a by 2 to mean, or a mean to plus a by 2 minus a by 2, whatever you go, sin theta will be how much? 1 by 2, because a by 2 by a will become 1 by 2. So 1 by 2 means theta is 30 degrees. So what is the minimum time? 30 by 360, 1 by 12, so t by 12. If you want to go from mean to extreme or vice versa, mean to any extreme, right or left, so you know x will become plus minus a. If x is plus minus a, that means sin theta will become 1. So theta will become 90. So time will become 90 by 360, that is t by 4. Clear? When now I'll do one thing. I'll take one question so that any confusion if there, it will be removed. Suppose they give you a question like this. Now you see the significance of this. Suppose this is x equals to a, this is x equals to minus a, and they have given position over here x equals to root 3a by 2, and here we have a position x equals to minus a by root 2. Now suppose they say particle is here at t equals to 0 and it is going this side. Let's mark this point, let's call this as P and let's call this point as Q. It is going this side. So they will say time taken to go from P to Q, minimum time, if you are going like this, will be how much? So how to solve it? See how easily we can solve. So first, as I said, first you will go this side. Now root 3a by 2, orally you can say root 3a by 2 means divide by A. Sin theta is equals to root 3 by 2. Root 3 by 2 means theta is equals to how much? 60 degree. So from here to here, what is the time? Theta by 360. So 60 by 360, T by 6. Clear? Now we know this time is T by 4. So we got this time. So this will become T by 4 minus T by 6. Right? Now let's see this minus A by root 2. What is the angle theta magnitude? Sin theta will be 1 by root 2. Sin theta 1 by root 2. So theta will become 45 degree. So 45 degree means this time will become 45 by 360. That is T by 8. So if you see time taken, first you will go from here to here. How much time you will take from here to here? First you took T by 4 minus T by 6. See from here, first you went this side. Then you came back to mean position. What is this time? From here to here, the time is T by 4. And then from here to here, how much time you will take? You will take T by 8. That's it. Suppose in question they have given time period is say 24 seconds. So now we can solve this. 24 by 4, 6. 24 by 6, 4. 24 by 4, 6. 24 by 8, 3. So 6, 6, 12, 3, 15 minus 4, 11 seconds. See, this way we can find the time. Clear? So moving back. So next thing, energy in SHM. Now energy in SHM at x equals to x, the energy, potential energy is half kx square, because force is of the form kx similar to spring force. So in spring force we know energy is half kx square, so same energy you will get half kx square here. Or k can be written as m omega square, because omega square is k by m. So in place of k you can always substitute m omega square. So energy is this value, potential. Kinetic energy is half mv square. What I said, v square is omega square a square minus x square. So either write half m omega square a square minus x square or half k a square minus x square. Now if you add both kinetic plus potential, you will get half k a square or half m omega square a square, which is constant. Okay, so total energy is constant. Now kinetic energy is varying with x as quadratic equation and the coefficient of x square is negative. So kinetic energy curve will be a down parabola with position. U is half kx square directly proportional to x square, quadratic in x and coefficient of x square is positive. So up parabola. So potential energy curve you can see is up parabola, kinetic energy is down parabola. At extreme positions, potential energy is maximum and kinetic energy is 0. I have drawn the blue graph by representing kinetic energy and yellow graph for potential energy. Now there is position, two positions are there where the kinetic and potential energies will be equal. Which one are the two positions? If you equate kinetic and potential energy, you will get x is equals to plus minus a by root 2. Very important point, at x is equals to plus minus a by root 2, kinetic energy and potential energy are equal. Means total energy is divided equally into kinetic and potential energy. Clear? Next we have important graphs in SHM. Now since acceleration is minus omega square x, so we have a linear equation, so straight line passing through origin with negative slope. So you can see the negative slope straight line graph. If you see v versus x graph, if you rearrange v square equals to omega square minus x square, a square minus x square. So on rearranging, you will get v square by omega a whole squared plus x squared upon a squared is equals to 1. So which is the equation of an ellipse. So on y axis we have drawn v and on x axis we have drawn x. So you can see this is an elliptical graph. Now with time sometimes graphs are asked. So suppose I take x is equals to a sin omega t. So v will become a omega cos omega t. Acceleration will become minus a omega square sin omega t because acceleration is minus omega square x. Kinetic energy is v proportional to v square and potential energy proportional to x square. So suppose I draw the graph of x. This is the graph of x, sine graph. So v you can see is cos graph, leads x by pi by 2. Acceleration, just flip the graph of x because acceleration is proportional to minus x. So acceleration is minus sin omega t. So graph will become flipped. Now kinetic energy is proportional to v square. V square means wherever v is negative, just make it positive by flipping. So you can see kinetic energy becomes like this. Potential energy is proportional to x square. So wherever x is negative, just flip and make it positive. So you can see potential energy. Now you can see one thing, x, v and a, they repeat themselves exactly after what time? Minimum time, capital T. See, x is going up, again goes up positively at t. V was initially plus maximum, again plus maximum is over here. Same with acceleration also. Acceleration was first going down, again it will go down after becoming 0 at t. But if you see the repetition of kinetic energy was maximum here, again it is maximum at what time? T by 2. So in one full cycle of SHM, kinetic energy, you can see there are 2 full cycles. Same with potential energy, there are 2 full cycles. Means the kinetic energy and potential energy will vary periodically with double the frequency of SHM. So frequency of kinetic energy and potential energy will be double of that of SHM, and time period of repetition will be T by 2. So if SHM has time period T and frequency omega, then kinetic energy and potential energy will vary periodically with a time period T by 2 and frequency 2 omega. Very, very important point. Next, sometimes we have shifted SHM. If suppose for my convenience, I don't take x equals to 0 as the mean position, I take x equals to x naught, any other point. So in that case, the case of shifted SHM, on the x axis, the mean position will be here. So we know acceleration is minus omega square x. In place of x, you will just substitute x minus x naught. So basically acceleration takes the form p minus qx, where p and q are constants, positive constants. So if you compare this, so you will get the mean position as p naught by x naught is equals to p by q. Why? Because mean position means acceleration 0. So if you get forms like this, acceleration sometimes written p minus qx. So what to do? Simply make it equals to 0. You get the mean position x naught as p by q. That's it. And omega, the coefficient of x is minus x is omega square. So omega square is q. So omega will be root q. Time period will be 2 pi by root q. That's it. So in such case, at t equals to t, if they ask you to write the position, so you will say x is equals to x naught. First you wrote a sin omega t plus phi, you will add an extra x naught. Why? Because now you are not taking the distance from origin, you are taking from x naught. So x is equals to x naught plus. So when you are writing the position from origin, so there will be x naught plus a sin omega t plus phi. Okay. So you have shifted origin case. So amplitude is a, no change in amplitude. Don't say that amplitude becomes x naught plus a. Amplitude is still a. Only it is the case of shifted SHM. So left extreme and right extreme. Earlier left extreme position was at minus a. Now it will become x naught minus a. Whatever values you had, just add extra x naught. As simple as that. Right extreme position, earlier it was a. Now it becomes x naught plus a. General position was a sin omega t plus phi. New position is x naught plus a sin omega t plus phi. V square you used to write omega square a square minus x square. Here you will say v square equals to omega square a square minus, in place of x, x minus x naught ka square. In any general SHM, whenever we write energy, we say Ke plus U is constant. Now at mean position we know kinetic energy is maximum, potential energy is minimum. At extreme position kinetic energy is minimum, potential energy is maximum. But wait here, it is not necessary that the minimum potential energy is always 0. So there are instances when the minimum potential energy or mean position energy is not 0. So if it is non-zero, how to find other values? Capital E, Ke max plus U min. Ke max, remember, is always half mv max square, and V max is what? Omega A. So you can always write it as half m omega square a square or half Ka square, always. So if the force constant is given for the oscillator is K and amplitude is A, so Ke max will be half Ka square always. Now this won't be the total energy. Total energy is Ke max plus U min. So suppose you know U min, so that value plus half K square will be the total energy. Now same total energy will be at extreme position also. But at extreme position kinetic energy will be minimum, and that minimum value will be 0, because you cannot cross the mean extreme position. That means there your speed will become 0. So Ke minimum is always 0. U minimum may or may not be 0. So simple words, you can say Ke minimum is 0. So potential energy at extreme position is always equals to total energy of SHM, because E is equals to this plus this. Ke minimum is 0. So maximum potential energy of SHM is always equals to the total energy of SHM. Understood? So remember this point. Next, linear SHM in spring block system. Okay, we have a very important case of spring block system, where we have a spring attached to a block and we have kept this end fixed, and suppose initially the block was at rest and we start applying a constant force F naught. So if you apply a constant force F naught, so what will happen? This won't be the mean position now. This spring is relaxed, so x equals to 0, but its speed is 0, so it won't be mean position, it is left extreme position. Why left extreme position? Because when the spring gets pulled, there will be a particular position where the external force F naught will be balanced by the spring force. So that position x will become F naught by k. By F naught is kx, so x equals to F naught by k. So this will be the mean position. And since we have one position where you have rest, so I said in SHM, the instantaneous rest position is called extreme position. On which side it is lying of mean position? Left, so this becomes left extreme. So simply we will say this is the amplitude. See how simple, this becomes the amplitude. For the resulting motion, this will be the amplitude of, so A will be F naught by k. Now we know mean position is exactly mid of two extremes, so other extreme will be on the other side. So again the speed will become 0 at which position? X is equals to x max. The maximum elongation of spring will occur where V is 0. So I will say this is also A. This is A. A is amplitude is how much? F naught by k. So x max, maximum elongation in the spring is 2 F naught by k. Without any calculation. V max, at mean position we have maximum speed of the block. If they ask maximum speed, no work energy theorem, nothing, directly in one line. V max in SHM is omega A. Omega is how much? For spring block system, remember omega is root k by m. So root k by m and multiplied by amplitude, which is F naught by k. So we get F naught by root mk. Simple. And this omega, which is root k by m, mind it is independent of presence of any constant forces acting on the block. Whatever constant forces act, it won't change the angular frequency of SHM. Okay. Now this thing, they will say sometimes that the block is suspended vertically and released from relaxed state of the spring. So here this case is exactly same as this, only in place of F naught vertical, now you have a constant force mg acting. So just replace F naught by mg. So you will see time period is 2 pi root m by k. If they say what is the maximum elongation in the spring, very simple, maximum elongation was 2 F naught by k, here you will write 2 mg by k. Okay. So everything will be same, just replace F naught by mg. Now comes when we have a combination of blocks with spring. Instead of a single spring, we have, combination of springs with a block. Combination of springs with a block. First we have series combination. So some important points regarding series, they are connected end to end, and the block, if you displace by x, these will be displaced by say x1 and x2. Now if you see the junction point P between them, they will sometimes ask that what is the displacement or amplitude of P. If they say that the amplitude of block is A, what is the amplitude of block of the point P, junction point P? So you should know that in spring, x1 plus x2 will be equals to A, x if they are in series, and spring force will be same for all, because spring is ideal, everywhere tension will be same. So K1 x1 is equals to K2 x2. So from these two equations, xp, the displacement of point P is same as that of the spring 2, so which is x2. So from these two equations you will get x2 is equals to K1x, x2 is equals to K1x by K1 plus K2. Clear? And in series, 1 by K equivalent, if you replace it by a single spring, 1 by K equivalent is 1 by K1 plus 1 by K2, 1 by K3, as many springs are there. Time period 2 pi under root m by K equivalent. If you have parallel combination, now parallel combination is represented in two ways. Either both the springs will be given on same side, both are as many springs, they are on the same side, or two springs on two sides like this. So in parallel, what we understand, if the block is displaced by x, each spring will be displaced by the same amount. So both the springs will be elongated by x. Here one spring will be compressed by x, one spring will be elongated, but displacement, direction also, see, same. This is compressed, so this is the displacement x. This is elongated, displacement x. So displacement is same for all. So x1 equals to x2 is equals to x. In such case, K equivalent becomes K1 plus K2. So as many springs, K1 plus K2 plus K3 and so on. Time period 2 pi under root m by K equivalent again. Now sometimes you will be seeing questions where they give that the spring whose spring constant is K and total natural length is L. So spring constant, mind it, is always inversely proportional to the natural length. It is also called as stiffness constant. Greater the length, lesser will be K. Okay, less stiff it will be. Lesser the length, more stiff it will be. So here, if it is cut into several parts, L1 is to L2 is to L3 and so on ratio, such that the total length L is the sum of L1, L2, L3 and so on. Then as I said, K into L is constant. So using that concept, KL will be equals to K1 L1 equals to K2 L2 is equals to K3 L3 and so on. So directly you can find the spring constant. First part will be K1 is K into L by L1, K2 K into L by L2, means K into total length divided by the length ratio for that part. That's it. Next we have springs having mass. Sometimes you will have spring also has mass. Now if spring also has mass and spring constant, so suppose I have taken the mass as ms, and if you displace the block, then each element of the spring will also have kinetic energies. Their kinetic energies will be different because different points will move by different velocities, right? So in that case, when we integrate and find, very important result, kinetic energy of the spring becomes 1 by 6 ms v square. If at any instant the block has displaced by x and has a speed v, then the spring energy will be half kx square like earlier, but kinetic energy of the spring at that instant will become 1 by 6 ms v square, where ms is the mass of the spring. So I can, if I write kinetic energy expressed as half mv square, so I can see half ms by 3 v square, means equivalent mass or effective mass of the spring can be taken as ms by 3. Block's mass is m, extra mass you have ms by 3. So when we write the time period, we know time period is 2 pi under root m by k. So effective mass will be block's mass plus effective mass of spring, which is how much? Ms by 3. So m plus ms by 3 divided by k. So this is a very important result, remember it. Next we have 2 block oscillator. If you have 2 block oscillator where there are 2 blocks and you compress or elongate and release it, so what will happen? It will keep on performing oscillations together with same frequency and time period. Time period will be 2 pi under root mu by k. So mu here is reduced mass, which is m1 m2 by m1 plus m2 for the system. Now here sometimes one question comes, which you will see generally people solve in very much lengthy way by conserving momentum and all. Direct in one line. If you see, initially the spring was suppose given relaxed, and now we give velocities u1 and u2 vector to the blocks in any direction. So when x will become x max, they will ask you find the maximum elongation or compression in the spring. So we know when x will become x max, both blocks should attain the same velocity, means their relative velocity should be 0. Because if relative velocity is not 0, that means they will further elongate or compress the spring. So relative velocity becomes 0. Now can you visualize something? This case is exactly same as perfectly inelastic collision, where if blocks have initial velocities u1 and u2, finally they attain common velocity, relative velocity becomes 0, they attain common velocity. So in that case, we know there is maximum loss of kinetic energy, and remember the formula half mu u relative square, that is half mu u1 vector minus u2 vector ka square. Now you will say what is the purpose of that thing over here? Yes. So when x max is attained, there is maximum loss in kinetic energy of the system. So if there is maximum loss in kinetic energy of the system during x max, where has it gone to? It has gone to give potential energy to the spring. So potential energy in the spring is half kx max square. It is equals to the loss of kinetic energy, which is half mu u1 vector minus u2 vector square. If they are initially moving in same direction, so u1 minus u2. If they are moving in opposite direction, u1 plus u2. So half mu is the reduced mass. Just in one line you will get the maximum elongation or compression. No need of writing work energy theorem and momentum equation. Directly by that you can get. Next we come to what we call as angular SHM. Angular SHM, in this what happens when the body is performing angular SHM, the center of mass of the body will move along a circular arc to and fro, circular arc, small angle. The arc will subtend small angle about the axis of rotation, but it will be under the influence of a restoring torque. And that restoring torque, just if we take analogy with translational SHM or linear SHM, here translational SHM force was proportional to x. Here torque will be proportional to theta. So theta is the angular displacement, which is to be taken very small and in radians from the mean position. If you take the mean position line as theta equals to 0. So from theta equals to 0 position, if the center of mass is displaced by a small angle theta, then restoring torque should be of the form c theta. I have taken mod because I have already told this torque is opposite in sense to theta. So magnitude wise torque is equals to c theta. Here c will be called as torque constant. There we had force constant, here we have torque constant. And we know torque is equals to I alpha, I axis about the axis of rotation into alpha. So here alpha magnitude can be written as c by I into theta. So just like A was proportional to x, here alpha is proportional to theta. So this term c by I becomes omega square. See the analogy. There it was k by m. K becomes force constant, becomes torque constant, mass becomes moment of inertia. So omega square is c by I. So omega will become root c by I. Time period will become 2 pi under root I by c. So 2 pi under root moment of inertia about the axis of rotation divided by the torque constant. When we apply the same concept, we get in case of simple pendulum SHM, you will see that it will keep on oscillating with a very small angular amplitude theta max. Theta max means where speed will be 0. Maximum speed will be at the bottommost position. Now you can take it as angular SHM also, and you can treat it as a linear SHM also, because since the oscillation is very small in angle, so this can be taken as almost a straight line, this portion. So this is the extreme position, this is the extreme position, and this is the mean position. So between mean position and extreme position, the gap you can say this is right extreme and this is the left extreme. So between these two you have this mean position, and this mean position and this extreme can be separated by A. Now what is A? You can say A is the arc length, L is the radius, theta max is the angle. So V max we can say at bottommost point the maximum speed V max is omega into A. What is omega? In case of simple pendulum, when we apply the concept of torque, we get omega as root G by L, or time period is 2 pi under root L by G. So here time period, if they say of SHM, we will say 2 pi under root L by G, and omega is root G by L. So if they ask you maximum speed, you will simply say maximum speed is omega A. What is A? A is equals to L theta max. So when you substitute, you get theta max root GL. Very easy way of finding the maximum speed at bottom position when we have small angular amplitude. Theta max should be in radians, remember this. Now moving on, time period as I said is 2 pi root L by G. Now here you should be aware of what is L over here. I said L is OCM. Again come back to the diagram. OCM, O is the point of suspension and CM of the bob. The separation between this is known as length of the pendulum. So here if you see length, I am taking this total. So what is that length? That length is the length of the thread or string plus the radius of the bob, because total distance I have to take from the center. So that's what I have written over here, that L is OCM, that is length of the string plus radius of the bob. Okay, if you are assuming that the bob is uniform. Now if L is comparable, there are some changes in simple pendulum questions. If you see that L is comparable with radius of earth, so if the length of the pendulum is so large that it is comparable with radius of earth, where you should know this value, very important, radius of earth is 6400 kilometers, then time period will become 2 pi under root L effective by G, where L effective is nothing but reduced length. Just like I told reduced mass, it is reduced length, L into Re by L plus Re. Okay. Now if L is very large than Re, two cases, L is very large than Re, for example infinitely long pendulum. Don't say that sir infinitely long pendulum so time period is infinite. No, you cannot use this formula there. You have to use this formula. So if L is very large than Re, then denominator will become approximately L. So denominator becomes L, LL cancels, so you will get Re only. So time period will become 2 pi under root Re by G. If you substitute the value of Re, this is a very important value which we get as 84.6 minutes. So an infinitely long pendulum has a time period of oscillation of 84.6 minutes. Second case, if suppose Re is very large, normal pendulums which we use, okay, there the length of the pendulum is very small than Re. So in that case, you will see that Re is very large, so denominator will become approximately Re. So Re and Re will cancel, so you will get L. So 2 pi under root L by G which we are using. So it is only for very small pendulums, and very large pendulum 2 pi under root Re by G. Clear? Now in our clocks and watches to measure time, we use a pendulum which is called a seconds pendulum. Whenever you hear the word seconds pendulum, so its time period is 2 seconds. So if you are using a simple pendulum as a seconds pendulum on earth's surface where the value of G is known, as 10 meter per second square. So length of the pendulum is approximately 1 meter. Why? Because G and pi square are approximately same. So if you square both sides and put t is 2 seconds, so length will approximately come as 1 meter. So 1 meter long pendulum will approximately give you a time period of 2 seconds on surface of earth, and mainly it will give that value at the poles. If you have studied gravitation chapter, you should know that at poles we take the value of G as 10 meter per second square. Now what happens if G varies? If G varies, like you go to depth or you go to height, you know the formulas for gravitation, or if we consider the effects of rotation of earth, so G changes, so time period is 2 pi under root L by G, so it will be inversely proportional to root G, that's it. Now in spring block system, I said that if there are other constant forces, it doesn't affect the omega, but in case of simple pendulum, since we have the concept of torque, apart from gravity, if other constant forces whose resultant is suppose F naught vector, other constant forces F naught vector, that is also acting on the CM of the bob, then in that case what happens, that you have to first see that the pendulum is performing SHM in which frame, or suppose inside a vessel or where. So in that case time period will be 2 pi under root L by G effective. We have to take G effective. How to take G effective? G effective is nothing but the vector sum, magnitude of vector sum of G vector plus F naught vector by M, that's it. G vector means G vector acceleration due to gravity, here I am writing as G vector, which is always vertically downwards, and whatever is the external force F naught vector by M, divide by mass and find the resultant, you will get G effective. Simplest way of solving. Suppose pendulum is performing SHM inside an accelerated vessel, that is its point of suspension is also accelerating with A naught. So suppose accelerated vessel is there, so pendulum's point of suspension will also, suppose the vessel is moving right, so point of suspension of pendulum is also moving right. If vessel is moving up down, so point of suspension is also moving up and down. So if the point of suspension of the simple pendulum accelerates with A naught vector, which is constant, then in that case what you are going to take as F naught vector, since it is in accelerated vessel, then with respect to vessel it will be non-inertial frame, you have to use F naught as nothing but pseudo force. Pseudo force is minus ma naught. Minus ma naught means pseudo force is always opposite to the acceleration of the frame. So if frame is moving right side, pseudo force will be taken back side. So in place of F naught by M, you can simply write minus A naught vector. Okay. So let's see some examples of this. For example, suppose this bob is inside a lift or a cart and or box, and this box has an acceleration A naught. So suppose A naught is upwards, so pseudo force will be downwards. So you have to take G plus A naught, because G is also downward. I said vector sum of G and F naught by M. So G is downwards and pseudo force by mass is also downwards. So you will get G plus A naught. If box is accelerating downwards, so pseudo force will be upwards. So F by pseudo force by mass will be A naught up and G is down. So effective will be G minus A naught. If cart is accelerating right or left, so suppose right, so pseudo force will be left. So F naught by M will be A naught horizontal, G is vertical. So when you take vector sum under root of G square plus A naught square, because this is vertical, this is horizontal, that's it. Suppose you dip this pendulum inside water or any liquid and it is performing SHM. Now in this case you have extra force B, buoyant force. So in place of mg, now you are having mg minus B, because buoyant force acts up. We are assuming that the density of the liquid is less than density of the bob. So G effective will be nothing but mg minus B by mass, means G minus B by M. So buoyant force by mass, if you put entire volume is inside, so you get G common 1 minus rho L by rho bob. Rho L by rho bob, because buoyant force is nothing but volume of the pendulum, because completely inside, into density of liquid into G, and mass is volume into density of the bob. So from here you get this value. Now sometimes students are troubled by, suppose the pendulum is kept in a box and it is moving down. So suppose acceleration is A naught, generally we have G sin theta, suppose we are taking A naught, any random acceleration, and the inclined plane has an angle alpha. They will say what is the time period of pendulum if it is made to perform SHM inside. So you will see that mg is down, pseudo force is opposite to A naught up. Now what is the angle between pseudo force and G? It is 90 plus alpha. So in that case you will take G effective as under root of G square plus A naught square plus 2 G A naught cos 90 plus alpha. And don't forget cos 90 plus alpha is minus sin alpha. So from here we can find G effective. Once you know G effective, time period is 2 pi under root L by G effective. Clear? Last concept of oscillations, which is damped oscillations. Damped oscillations means here the oscillations are slowly fading away or dying. That means amplitude and energy of the SHM will fade away exponentially with time because of presence of some forces, non-conservative force like viscous force or kinetic friction. So such a force has, if such a force is of the form directly proportional to speed and opposite in direction, so damping force is vectorially expressed as minus BV vector, then only amplitude and energy will fade away exponentially with time. So in that case, if the initial amplitude was A naught and initial energy is E naught, so at time t the amplitude becomes A naught e to the power minus gamma t, and energy at time, energy is proportional to A square, so energy will become initial energy E naught into e to the power minus gamma t ka whole square, so that 2 will multiply, so minus 2 gamma t, where gamma is B by 2m. B is called here as the damping coefficient, gamma is called as the damping constant. So B by 2m, m is the mass of the oscillator. So here this is how energy and amplitude will vary. You can see a exponential curve. Now there is a simple concept over here, exponential curve. This is basically just like we have radioactive decay, which is first order reaction. In first order reaction, very important point, first order reaction concept is the fraction remaining in equal time intervals is always what? Equal time intervals, fraction remaining is equal. So what we can say, that if fractional amplitude or energy remaining at t equals to t naught is f, then in next any time interval t naught, suppose f is the amplitude remaining, means amplitude by initial amplitude, that is f. In the next one, the fraction will be same of the previous one. So now fraction will become f of f, f square. Next it will become f of f of f, f square. So that way we can say that the fraction remaining will be f to the power n after n t naught time. So in t naught time, if fraction remaining is f, then after n t naught time fraction remaining will be f by n, f to the power n. So basically you can say that if suppose in 2 seconds they say that the amplitude became half, in next 2 seconds it will become half by half, so fraction remaining is 1 by 4. So in next 2 seconds it will become 1 by 4 by 2, so that will become 1 by 8. So in general, after n half lives or n times of 2 seconds, how much will remain? A naught by 2 to the power n. So that is what I am trying to say over here. Okay. So what else we should know about damped oscillators? As I said that apart from a normal oscillator where we have a spring and block, as the block is moving, suppose it is displaced by x, has a velocity v and acceleration a, there are forces kx backwards and the viscous force bv backwards. So if you write Newton's second law, force is equals to mass into acceleration, force and acceleration are shown opposite, so you will use the equation as bv plus kx is equals to minus ma. If you want to write a differential equation for this damped oscillation, so acceleration is d square x by dt square, so m d square x by dt square plus bv, v is dx by dt plus kx is equals to 0. Now in this also you get form like SHM, only thing is that the amplitude is time varying. So x is 80 sine omega dt plus phi. Here omega d is the frequency of damped oscillator, which is not same as root k by m, it will be slightly less than that. So omega d is under root of omega naught square minus gamma square. Gamma I told b by 2m, so omega naught square minus gamma square under root, this will be the damped oscillator frequency, where omega naught is what? Root k by m. Okay. Now if you want, in case of damping, oscillations have to occur. So if it has to occur means omega d should be real value. Omega d will be real means omega naught should be more than gamma. If omega naught is very large than gamma, there will be very slight damping or light damping. Oscillations will take place. It will fade away very slowly. If we have critical damping is that case where there is no oscillation. If you release the block from the extreme position, it will come to rest and after that it won't oscillate. So no oscillation means omega d is 0. Omega d 0 means condition is omega naught should be equals to gamma. So B by 2m should be equals to root k by m. Simple condition you can find. If omega naught is less than gamma, then omega d will become unreal, means it can never oscillate. So that is called as over damping. Clear? Over damping, critical damping. Light damping means gamma is very small than omega naught. Now suppose the oscillations are fading away or dying because of loss of energy due to viscous force. So to restore these oscillations, we need to apply an external driving force which should also be periodic. If we apply that periodic force, and if we want maximum transfer of energy by the driving force to the oscillator, then maximum transfer of energy or maximum amplitude will be when the external driving force frequency equals the natural frequency of the oscillator. This condition of frequency matching is called as resonance. So here we have shown some graphs. Undamped oscillator performing SHM, you can see undamped oscillator means SHM, where time period is 2 pi by omega naught is root k by m. But if you have damped oscillator, the amplitude is varying exponentially, decreasing. So the sinusoidal graph is contained within the envelope of the amplitudes like this. So fades away. If you have over damping, from extreme position it starts and after long time it will come to rest. If we have critical damping, it starts from the extreme position and comes to rest in the least time, which is t by 4. You can remember it as time gap between extreme to mean position. What is that? T by 4 na? So t by 4 time it will come and stop. There won't be any oscillations further. Okay. Now we move to what we call as waves. Waves, what we know, waves is nothing but any form of disturbance produced by a source and it is spreading in a medium or propagating in medium, which is transporting energy and momentum without transportation of matter from one point to other. If material medium is certainly required and that material medium should have inertia and elasticity, then only it can propagate the wave further, then such a wave is called as mechanical wave. For example, we have string waves, sound waves, etc. But if we have waves which do not require material medium, they can move in even in vacuum. Such waves are electromagnetic, whose example we can take light. If the wave or disturbance is propagating, so it will vibrate all the particles of the medium, or at every point there will be some disturbance, right? If you are talking of mechanical waves. So that disturbance, those vibrations, if those vibrations are at any point perpendicular to the direction of wave propagation, then such a wave is called transverse wave. And example is string wave. EM waves are also transverse, non-mechanical, and in that case we don't have particles. In vacuum we don't have particles, but their electric and magnetic field, they oscillate. So something should be varying perpendicular in direction to the wave propagation. So what varies in case of EM waves? There are no particles, there are time varying electric and magnetic fields which oscillate or vibrate perpendicular to the direction of propagation. So such type of waves are transverse waves. If the vibrations are along the wave propagation to and fro, like in sound waves, the air columns will vibrate front and back if the wave is moving, then in that case the waves are called longitudinal, whose example is sound. Now whenever we have disturbance, mathematically we represent it as a wave function, which is a function of x and t. What is x and t? Suppose the wave is propagating along x-axis, then if we take any point of the medium as x equals to x, at time t equals to t, the disturbance produced at that point is called as y. So mathematically, when we have a traveling wave means it is continuously transferring energy from the source till infinity, non-stop, without any loss, energy loss. So those waves are called as traveling waves. So traveling waves, the expression for the function is of the form ax plus bt. If you see the empirical form, it is ax plus bt. Now ax plus bt, a and b can be positive, negative, whatever. So a and b, if a and b are of opposite signs, then the wave is said to move along positive x-axis. If they are of same sign, both positive or both negative, the wave is moving along negative x-axis. And for the wave to be representing a traveling wave, as I said, it should be finite for all values of x and t. So for all x and t, it should have a finite value. So it should have a form of ax plus bt, where a and b can be positive or negative, anything, and this should be finite at all positions. There should be no loss. The wave pulse does not change in shape, it simply gets transported from one point to other, carries, okay. But this expression ax plus bt form should be there, where again third time I am repeating, a and b can be both positive, both negative, one positive, one negative. when they ask you wave speed, nothing but coefficient of time divided by coefficient of x, just take the mod. So mod of b by a will give you the wave speed. The traveling wave, if it is a harmonic wave, now if you have a mechanical harmonic wave means the particles of the medium, they will perform vibration. Which type of vibration? SHM. So they perform SHM. In such case, the equation will be just like that of SHM. The wave function will be a sine kx plus omega t plus phi plus minus anything. I have written both the values, plus minus. Okay. So this form. Now k and omega. K is called as the wave constant, which is 2 pi by lambda. Lambda is wavelength. Omega is 2 pi f. F is the frequency. Wavelength is the distance travelled by the wave in the medium by the time it completes one cycle of disturbance. So that wavelength 2 pi by lambda. Now wave speed, I said, is the coefficient of t by coefficient of k, x, take mod. So it will be omega by k. Omega by k, and if you put omega as 2 pi f and k is 2 pi by lambda, so we can write v is equals to f lambda. Frequency into wavelength is the wave speed. Very, very important point. And each point of this, each particle of the medium in case of a harmonic wave will perform SHM. So each particle performs SHM, same frequency, same amplitude. Every point will be disturbed by the same amount from mean position. With how much amplitude? A, and frequency f. So wave amplitude is A, that means the amplitude of each particle of the medium is A. Now in this case, you will be asked sometimes, find the speed of any particle. Now suppose we have to find the speed of any particle. So what do? We partially differentiate the wave function with respect to time, because for particle the position x is fixed. X is the position or location of the particle on x-axis. So it will vibrate along y-axis. So del y by del t. Now since it is performing SHM, we will use the equation of SHM. We know V is omega under root a square minus displacement from mean position. So displacement from mean position is y. So V equals to omega under root a square minus y square. This is the particle velocity at any position at time t equals to t. If they ask you accretion of the particle is nothing but partial derivative of velocity, which is just like SHM minus omega square y. Why we are taking y? Because the displacement, SHM, we used to take the displacement from mean position. So displacement from mean position is y. So minus omega square y. Okay, in transverse traveling wave, if they ask you what will be the direction of particle at any given instant. So particle velocity and wave velocity are related by this mathematical formula. V particle is minus V, wave velocity, multiplied by slope of wave pulse at a point. So if the wave pulse or the shape of the pulse is given, at any point see whether the pulse is going up or coming down. If it is going up, positive slope. If it is coming down, negative slope. Clear? V, you will take positive if wave is moving right side, negative if wave is moving left side. So from here, if you get the particle velocity as positive, this means particle is moving up. And if it is coming negative, it means particle is moving down. So to make this thing clear, I'll just take a simple example and I'll tell you another shortcut method of doing that. So suppose we have a wave pulse, snapshot given, and we are seeing some particles. Let's take here. So we want to check where they are moving. So if I name these particles as 1, 2, 3 and 4, and suppose the wave is given moving right side. Okay. So first method, now see, particle velocity is minus V into slope. So V, you can see it is given right side to positive. So Vp will be proportional to minus slope. Now you can see at point 1 graph is going up, point 4 also graph is going up. At 1 and 4 graph is going up, so slope is positive. So this means particle velocity negative, that means particles are coming down. At 2 and 3, both you can see the graph is coming down. Graph is coming down, slope will be negative. So particle velocity is proportional to negative slope, so minus minus will become plus, that means going up. So we can say at these positions, the particle at 1 and 4, they are coming down. As the wave is going right side, these particles are coming down. And at 2 and 3, they are going up. Clear? Alternate method you can do is what? You just draw the waveform at two different times. Remembering that wave pulse does not change its shape, it simply get transported. So suppose I have drawn this graph at any time t equals to t naught. Suppose t equals to t naught. Now what you will do, you will simply shift this graph. Where is the wave going? Wave is going this side. So the pulse has to be shifted towards right side. So just shift the pulse to a new position towards right, remembering that shape, peak values, they are not going to change, like this. Can you see? So this dotted graph will represent at time t greater than t naught. So earlier, let's now mark the particles. Earlier, particle 1 was on this bold graph. Now it will come to the dotted graph. So where will it has to come? From bold to dotted, it has to come down. If you see point 2, earlier it was at the bold graph. Now to dotted graph is not below, dotted is up. So it has to go up. Now if you see point 3, bold graph to dotted graph, that means it has also to go up. Now if you see point 4, earlier it was on bold graph, now it has to come to dotted graph. So it is coming down. So this way also you can compare and see same result. I hope it is clear. Next, okay, apart from that, next thing, two particles, if they ask you for phase difference, two particles if they are located at x1 and x2 points and at same time instant you are observing them at t equals to t. So phase difference between them will be k delta x, delta phi will be k delta x, delta x will be called as path difference x2 minus x1. So phase difference is k delta x, k is 2 pi by lambda. If I see the vibration of a given particle, say at x equals to x at two different time instants, here I were observing two different particles at same instant, now I am observing one particle at two different instants t1 and t2, then we have phase difference and time difference. So phi was omega t, so delta phi will be omega delta t. There phi was kx, so k delta x. So delta phi phase difference will be omega times delta t. Omega is 2 pi into f. Now whenever we have delta phi as 2 and pi, means 0, 2 pi, 4 pi, 6 pi, 8 pi and so on, then we say that the particles are in phase. And whenever we see that there is odd multiple of pi, then we say that the vibrations are out of phase. Okay. Speed of transverse wave. Now transverse wave, if you are taking string wave in a string, the speed is given by under root t by mu. T is tension, mu is the linear mass density or mass per unit length. Mass per unit length is sometimes also written as density multiplied by area of cross section, because mu is mass by length and rho is mass by volume. So mu is rho into A, remember this. Now they will ask you what is the time taken by the string wave to move from one point of the string to the other. Suppose length of the string is L. If suppose t and mu are same at all points, so v will be constant, so time will be directly L by v. Okay. But sometimes what will happen, suppose we have a uniform massive rope. Now in this case, when we give a jerk to the string at the lower end, this transverse wave will move up. So here if we move x distance up, the wave speed will be root t by mu. Tension over here will be the hanging weight below it, and if you divide by mu, the speed comes of the form root gx. If you compare and see, root gx is nothing but of the form u square plus 2ax. So acceleration of the wave pulse, which is uniformly accelerated motion. So you have uniformly accelerated pulse which is going up with an acceleration. Compare and see, it is g by 2. So very, very important, acceleration of the pulse is g by 2. So if they ask you what is the time taken for the string wave to go from A to B or come back from B to A, symmetric motion A to B or B to A, the time period will be under root 2L by A, because L is equals to half AT square. Initial velocity was 0. So root 2L by A, that will become 2 root L by G. Important formula, 2 root L by G. Apart from this, we have average power and intensity transmitted by the wave. They ask you what is the average power and intensity transmitted. So power, very simple way of remembering. Beta, what is power? Energy by time. So average power, energy. Remember SHM, half m omega square A square. I tell to students how to remember easily. Half m omega square A square. This is for SHM, divided by time. One full cycle, so capital T. Now you know what we can say from here. Mass. Mass can be one full cycle, mass per unit length is mu, full cycle multiplied with the length lambda, and we know 1 by T is F. So F lambda, F will go up, F lambda will become how much? V. So you are getting half mu V omega square A square. A simple way of remembering this power expression. Half mu V omega square A square. If they ask you average intensity, intensity is power by area of cross section of the string. So if you divide mu by A, I said mu by A is rho. So same expression, only here mu, here rho. Half rho V omega square A square. Now remember that if medium is same for two different waves, if they are saying medium is same, what is same? V. V is a property of medium, it will remain the same. If source is same for two waves, then what is same? Omega or frequency. Frequency is a property of source. This thing should be kept in mind. Next, we have standing waves. Whenever we have traveling waves which are moving along opposite direction, their superposition will give you what is called a standing wave, in which what happens, every point of the medium does not vibrate. There are certain points which don't vibrate at all. That means the medium gets divided into segments or loops, and vibrations of each loop will be confined in that loop only. It will not be able to cross that loop and go ahead. So that's why it is the name standing wave. Medium vibrates in the form of loops. Now remember that the original traveling waves, they are moving throughout. Both waves are moving, but it will give an impression that the net energy is getting confined in certain regions which are known as loops. So here, if we have the two waves, for example, sine, both I have taken sine. I can take cos also, doesn't matter, sine or cos, whatever. If I take example sine kx minus omega t, sine kx plus omega t, resulting wave equation, when you add sine a plus sine b formula, if you use, you get 2a sine kx cos omega t. Now this is the amplitude part, 2a sine kx cos omega t is called as the phase part. So there are certain points, nodes, which I said they will always be at rest, unlike traveling waves. All points in traveling waves vibrate, here nodes do not vibrate. So nodes where y or disturbance is always 0. So if you put y is equals to 0, you get the positions of x as 0, lambda by 2, lambda, 3 lambda by 2 and so on. Then there are positions antinodes where the amplitude 2a sine kx is maximum, means plus minus 2a. So maximum, so these will come exactly in between two nodes. So antinodes are positions exactly in between two nodes. So remember, two successive nodes are separated by lambda by 2. A node and a successive antinode are separated by lambda by 4, right? And two successive antinodes are again separated by lambda by 2. So nodes and antinodes, I have shown it in diagram. So you can see the string in which wave is moving in one direction, other direction, when they superimpose, like you take a string and you give it a jerk, you will see that there will be vibrations in the spring. There can be single vibrations, there can be multiple vibrations, many loops can also form. So suppose the string is vibrating like this. So at any instant, either it is going up or coming down and so on. The next loop also, either it is down or going up and so on. Now what you are seeing, that vibrations in the adjacent loops are always out of phase. If one loop vibrations are up, other one down, then the next one again up. Means in alternate loops, the vibrations are in same phase. All points of the same loop and in alternate loops have the same phase. Their phase difference is 0. So in case of standing waves, you have only two phase difference possible. One is 0 and one is pi. So how do you understand where to take what? How do you understand where to take what? So vibrations, if they are in the same loop, all points, or in alternate loops, they are always in same phase. Phase difference is 0. And if the points are in adjacent loops, then they will have a phase difference of pi. So in one loop going up, again down. So here pi pi, here pi pi. So here and here 2 pi. 2 pi means same phase. Clear? So this length, the separation between successive nodes, this is called as lambda by 2, is known as the loop length. One loop is the region between two successive nodes. Okay. Next, natural frequencies of vibration. So if you take a string and fix at both ends and you pluck anywhere in the middle or any point, so waves will go, hit the ends, reflect back, reflected and incident waves will superimpose and they will give a standing wave. The loop, the string can vibrate in single or multiple loops. The simplest form is a single loop vibration where the two ends will be nodes. The two ends will be always nodes. Now in single vibration, the frequency, fundamental frequency will be V by 2L. If it is vibrating in n loops, then Fn is equals to Nv by 2L. Fundamental frequency means one loop vibration. Here n loops, in nth mode there will be n loops, so Nv by 2L, and V is what? Root T by mu, so N by 2L under root T by mu. This is the frequency, and you should remember two important terms. One is called integral multiples of F1. The integral multiples of F1 are called as harmonics. That means F1 is first harmonic, 2F1 will be second harmonic, 3F1 is third harmonic, 5F1 is fifth harmonic. But frequencies above over F1 are called as overtones. So suppose I take F2. F2 is first overtone. It can, if it is 2F2, 2F1, it will be second harmonic, but overtone wise, when you are counting above fundamental, you call them as overtones. So second frequency is always the first overtone. Third frequency is always the second overtone. Nth frequency is always the n minus 1th overtone. This should be remembered. Now, sometimes you will see that if frequency of any source, example a vibrating tuning fork, is brought near the string and it matches with any of the natural frequencies of the string, this is the condition of resonance. So the string will start vibration in that many loops. Now, one more term sometimes you will see in question, kindly remember, this is called as 2F1. 2F1 is known as an octave. 2F1 is called octave. So if they say that one frequency is octave of the other, means it is double. So V of transverse wave, when we want to determine the speed of a transverse wave, we use an experimental setup called sonometer wire. In sonometer wire, we use clamps over here and one of the bridges below, it can be moved, right? So we can adjust the length. We are having some load here which will provide tension. So we bring a vibrating tuning fork F0 and then we check for resonances in this segment, just behaving like a string fixed at both ends. So sonometer wire, this length is behaving like a string fixed at both ends. So when you bring a frequency F0 which matches over here, suppose successive resonances with the same tuning fork are observed at length L1 and L2. Once you keep the length as L equals to L1, you can measure the length by a scale, then you change it to L2, and 2 times if you see resonances with the tuning fork, then the wavelength can be calculated as 2 times L2 minus L1, and the speed we know is F into lambda, so it will become 2F0 L2 minus L1. So direct questions can be asked if successive resonances are observed for length L1 and L2 of the string, the speed of the wave will be 2F0 L2 minus L1. F0 is the frequency of tuning fork which will be known to us. Clear? Next, sound waves. Sound waves, they are longitudinal waves. In longitudinal waves, the speed formula is root E by rho. E is elastic constant. If you have a clamped rod in which the vibrations are taking place, we will use E as Young's modulus. But in a voluminous medium, you will take E as bulk modulus. Okay. Now, the elasticity in solids is very large compared to liquids than in gases. Hence, in speed comparison also, sound is more in solids, very large compared to liquids than in gas. So sound travels faster in solids than in liquids than in gases. Okay. So this thing should be remembered. Now if we have an ideal gaseous medium, so in ideal gases, bulk modulus, in previous lecture we had studied bulk modulus for an ideal gas. If we write B is equals to X times P, X is polytropic constant. Laplace found that the conditions are adiabatic. So bulk modulus is gamma p. He found that the conditions of sound propagation were adiabatic. So B is equals to gamma p. So V sound, if you put E as bulk modulus which is gamma p, so it becomes root gamma p by rho. But we know for ideal gas P by rho is RT by molecular weight. So it can also be written as gamma RT by molecular weight under root. So this, in a given gas, If molecular weight is fixed, so V sound will be directly proportional to root T. If you find it for air, treating air as a diatomic mixture, so 330 meter per second comes the approximate speed at 0 degree Celsius. So this is Laplace formula. Earlier Newton had given a formula where he assumed isothermal condition and he got V sound as root P by rho, which is wrong. Actually it is root gamma P by rho. Gamma is the adiabatic constant, Cp by Cv. Clear? Now when we used to use this equation sometimes at 0 degree Celsius and at other temperature theta, which is very small, say 4 degree, 5 degree, 10 degree. So in that case, when theta is very small compared to 273, if this value is very small, then in such case we can use, as I said, V is proportional to root T. So V1 by V2 will become root T1 by root T2. So if I write in Celsius, so V theta is equals to V naught into Celsius. I have converted theta plus 273 by 273 root. So when theta is very small, we can apply binomial, multiply the power, it becomes V naught into 1 plus theta by 546. So when you are given small temperatures which are very small compared to 273, if theta is in Celsius, you can directly use V theta is equals to V naught into 1 plus theta by 546. Clear? Next, equation of travelling harmonic longitudinal wave. Now when we have transverse wave, we saw y was the displacement of the particles perpendicular to the wave motion. But in longitudinal waves, we represent the travelling wave by two different wave equations, two forms, because as the longitudinal wave like sound will propagate, then the particles or air columns will displace as well as there will be change in pressure or fluctuation in pressure. So sometimes we write it as displacement wave, sometimes we write it as pressure wave. When you are representing y as the displacement of the particles, medium particles at any position x equals to x, t equals to t, same expression, S naught is the maximum displacement, sin kx minus omega t plus phi. This is called displacement wave. But if you write the pressure fluctuation, it has been derived and seen. So delta P, pressure fluctuation from its natural value, or natural value we take as atmospheric pressure. So pressure fluctuation or change from its natural value at any position x equals to x at t equals to t is given by the expression minus b del s by del x, b into del s by del x partial derivative of s with respect to x. So when you differentiate it, we get minus bk s naught cos kx minus omega t plus phi. So one is sine, one is cos. This equation is called as pressure wave, this is called as displacement wave. One is sine, one is cos, so they always differ in phase by how much? Pi by 2. Very, very important question. Pressure wave and displacement wave always differ in phase by pi by 2. And what is the maximum pressure fluctuation? Delta P max, which is called as the pressure amplitude. Pressure amplitude is Bk S naught. Pressure amplitude is Bk S naught. B is bulk modulus. K is 2 pi by lambda. K is 2 pi by lambda. B is the bulk modulus. And S naught is the displacement amplitude. So very important relation. Now delta P is pressure fluctuation at any point, which is pressure at that point minus atmospheric pressure. If it comes as positive, means pressure is more than atmospheric pressure there, that region is called as compression region. Wherever you see pressure is more than atmospheric pressure, means delta P positive, it is compression. Wherever delta P is negative, that means pressure at that point is less than atmospheric pressure, that will be called as rarefaction. Clear? Next, standing longitudinal waves in organ pipes. Now when two travelling waves superimpose from opposite direction, they form standing waves. In organ pipes, there are cylindrical pipes. One is closed organ pipe, one is open organ pipe. Closed organ pipe which is closed at one end, open at the other. So closed end is a displacement node or a pressure antinode. Open end is a displacement antinode or pressure node. So here standing waves are formed. The fundamental frequency is when we have the length of the organ pipe equals to lambda by 4. Node and antinode, simplest form. Separation between node and antinode is lambda by 4. So lambda becomes 4L. So F becomes V by 4L. Fundamental frequency is V by 4L. In this case, only odd harmonics are present. So F2 will be 3F1. Now mind it, it is overtone n minus 1. So F2 will be 3F1 means third harmonic, but first overtone. F3 will be 5F1. That is fifth harmonic, but overtone will be second, and so on. So 2n minus 1th harmonic, so nth frequency is 2n minus 1th harmonic or n minus 1th overtone. If we have open organ pipe which is open at both ends are always antinode, middle node. So fundamental form will be this one. So antinode, antinode, middle node. So this is lambda by 4, this is lambda by 4. Total will become lambda by 2. Lambda by 2 is L. So lambda will be 2L, frequency will be V by 2L. This is fundamental frequency. In closed organ pipe V by 4L, here V by 2L. In this all the frequencies are present. So nth frequency is n times F1. Overtone n minus 1 and frequency is nth harmonic. Here which harmonic it was? 2n minus 1th harmonic but n minus 1th overtone. Here it is nth harmonic but n minus 1th overtone. Overtone is just as I said, keep on calculating above F1. F2 is first overtone, F3 is second overtone, that's it. And harmonics are integral multiples. Now, sometimes you will see practical pipes, their diameter is comparable to the length. In that case, it is observed that the antinode which has to be formed at the open ends, they are formed slightly outside. So in that case, whatever formula we are using L for frequency and all, there you have to change the length, effective length you have to take. In place of L, you will take L plus E. If there is a closed organ pipe, only one end correction, the L plus E. If open organ pipe, both ends antinodes will be shifted outside, so L plus 2E. This is to be taken as the effective length, where E is called as the end correction, whose value has been calculated as experimentally as 0.3 D. If D is the diameter of the pipe, E is 0.3 D. Okay. Now speed of sound. Speed of sound is experimentally determined by a device, resonance column. It is a cylindrical pipe which is open at both ends. It is dipped in water. The water level can be varied by dipping it up and down. Now you can see here air column is formed, here water column. Total length is capital L. We take this surface of water over here. This is like behaving like closed end. So this part, on the upper part, this will behave like a closed organ pipe. So it is behaving like a closed organ pipe, and we bring a tuning fork and see successive resonances. Successive resonances will occur for what lengths of LA? First will be lambda by 4, second 3 lambda by 4, third 5 lambda by 4 and so on. So successive resonances will be in the ratio, odd number ratio, 1, 3, 5, 7 length. So length of air column, but there is a condition, length of air column should be less than equal to capital L. So they will say how many resonances you can observe with F0. So first you find wavelength. If you know the wavelength, find the lengths, lambda by 4, 3 lambda by 4, 5 lambda by 4 and so on. So those lengths should be less than capital L. So you can see how many resonances will be observed. Okay, so you can change LW and keep on seeing how many resonances can be observed here. Now in this case also, suppose I have two successive resonances at LA is equals to L1 and LA is equals to L2. So just like sonometer, we here also we get the same result. If successive resonances occur for L1 and L2, then lambda is calculated as 2 times L2 minus L1. So V will become 2F0 L2 minus L1. So same formula, experimental determination of speed of sound or experimental determination of speed of transverse wave. Same formula you are getting 2F0 L2 minus L1. L1 and L2 are the successive resonance lengths and F0 is the frequency of the tuning fork. Now last point we come to what is called as beats. Sometimes we see that sound, when we hear sound, we can hear the variation in its intensity. At a given place, intensity will vary with time. So that waxing and waning, waxing means increasing, waning means decreasing of intensity of sound is called beats. When does it occur? When we have traveling waves which are differing slightly in frequency and they are superimposed. So traveling waves differing only in frequency, their superposition gives us beats. Intensity of sound varies periodically with time, and the time gap between successive maximas of intensity is called as beat time period. Beat time period is given by 1 by F1 minus F2 magnitude. Beat frequency is just the reciprocal F1 minus F2. So resulting wave is still a traveling wave propagating with, now resulting wave will be a traveling wave. They will ask you what is the resulting wave speed, frequency. It will be average, that is F1 plus F2 by 2. I have explained over here. You can see that if superposition of the waves taken are A sin kx plus 2 pi F1t and A sin kx plus 2 pi F2t. So here when we take the resulting wave equation, you will add both. So you will get sin A plus sin B. So 2 sin A plus B by 2 and cos A minus B by 2. So you can see the terms here. So this part is the amplitude part. This whole part is the amplitude part, which is time varying amplitude. Okay. And the amplitude is varying with this frequency, right? So you can see the amplitude cosine graph I have drawn here. So this is time period of variation of amplitude. So what is that? Reciprocal of frequency. So 2 by f1 minus f2. This is the time period of amplitude. Amplitude will be repeating itself after here. But intensity, if you see, is proportional to square of amplitude. So if intensity is proportional to square of amplitude, that means that intensity graph will be like this, make the negative ones positive. So here you can see intensity maxima is again repeated here. So this is the beat time period which I said, it is half of this capital T, T by 2, so it will become 1 by f1 minus f2. So beat frequency will be f1 minus f2. Understood? So if you see the overall waveform at any position, suppose x equals to 0, I am observing, overall waveform if you see, so you have a sinusoidal wave which is moving, and you are seeing that this is the amplitude part which is fluctuating. So y will vary between these two values, plus 2a and minus 2a, sinusoidally. So this is the waveform of the beats. I hope this portion is clear to all of you. So that will be all for this lecture. Thank you.